Assalamualaikum warahmatullahi taala wabarakatuh. My name is Azim Hakimi Benzu Al Zulkifli, matrix number A82300506. So today in this video, our group will be presenting about application of differentiation, to be more precise, rate of change. So this is all of our group members. So I will start with introduction. Derivative can be used to express the rate at which quantities change. One of the main uses of derivative is determining the rate at which of one quantity change in relation to another. The chain rule can also be used to calculate the rate at which a function changes in relation to another quantity. A change in quantity with respect to time is typically used to define a rate of change. For instance, the derivative of speed denotes velocity, so the rate of change of speed with regard to time is represented by the formula ds over dt. The rate at which distance changes in relation to time is another illustration. Similarly, the rate of change of y with respect to x is given by dy over dx of fx. If a quantity, say y, changes with respect to another quantity x, such that y equal to fx. Therefore, the rate of change of y with respect to x is represented by d over dx fx for the function y equal to fx. Alternatively said, the derivative of y with respect to x is dy over dx. If the rate of change of quantity dy over dx increases, then it is represented by positive sign. If the rate of change of quantity dy over dx decrease, and then it is represented by negative sign. If two variables, say x and y, change with respect to another variable t. In example, if x equal to ft and y equal to ft, then according to the chain rule, dy per dx equal to dy per dt multiplied by per dx per dt, where dx per dt is not equal to 0. Hence, we can calculate the rate of change of variable y with respect to x by finding the rate of change of both y and x with respect to t.
Assalamualaikum. My name is Ahmad Idham bin Muhammad Zaidi. Number matrix AA231894. Today, I will present about filler table for part A and part B. For part A, the rate of flow of oil through a pipeline is given by the function Ft equal to 20e power of negative 0.3t, where F is the flow rate in barrels per hour and T is the time in hours. Determine the rate at which the flow rate is decreasing after 2 hours. Facts. Number 1. The rate flow of oil through a pipeline is given by the function. Number 2. F is the flow rate in barrel per hours. Number 3. T is the time in hours. Ideas. We can solve this problem by using rate of change formula equal to dy over dx equal to dy over dt multiply dt over dx. Learning issue, the rate at which the flow rate is decreasing after 2 hours. Action plan number 1, use rate of change method to solve this problem. Number 2, substitute t equal to 2 into the equation to solve it. Part B. For part B, in a power plant, a cylindrical pipe in a heat exchanger system is subjected to varying temperature, causing it to expand or contract. Although not a sphere or cube, consider the pipe's cross-sectional area, which is circular and thus relates closely to the sphere geometry. The diameter of the pipe increases at the rate of 0.01 cm per hour due to thermal expansion. Calculate the rate at which the cross-sectional area of the pipe is increasing when its diameter is 50 cm. Discuss the implication of this expansion on the efficiency of the heat exchanger system. Facts. The cross-sectional area A of a circular pipe is given by the formula A equal to pi d power of 2 over 4. Number 2. The diameter of the pipe increases at a rate of 0.01 cm per hour due to thermal expansion. Number 3. The diameter is 50 centimeters. Ideas. Number 1. Calculate the rate at which the cross-sectional area of the pipe is increasing. Number 2. Determine the implications of this expansion on the efficiency of the heat exchanger system. Learning issue. Number 1. Understanding the relationship between diameter and cross-sectional area. Number 2. Differentiating the area with respect to time to find the rate of change. Number 3. Exploring how change in pipe dimension affect heat exchanger performance and system efficiency. Action plan number 1. Differentiate the area formula A equal to pi d power of 2 over 4 with respect to time. Number 2. Calculate the rate of change of the area when the diameter is 50 centimeters. Number 3. Analyze the impact of the pipe's expansion on heat transfer rate, pressure drop, structural integrity, and thermal stress.
Assalamualaikum warahmatullahi wabarakatuh. My name is Muhammad Effendi Mahatta, metric number AA 231931. Today I'll be presenting about problem statement for part A. The statement is the rate of oil through a pipeline is given by the function Ft equal to 20 exponent to the power of negative 0.3t, where F is the flow rate in barrels per hour and T is time in hours. Determine the rate at which the flow rate is decreasing after 2 hours. Solution of case study for part A for the function Ft equal to 20 exponent to the power of negative 0.3t. First, we need to differentiate the function with respect to t, which will give us f prime t equal to d over dt times 20 exponent to the power of negative 0.3t, which then we will leave f prime t equal to 20 times negative 0.3 exponent to the power of negative 0.3t. The answer then we will get is f prime t equal to negative 6 exponent to the power of negative 0.3t. Next, we will substitute t equal to 2 into derivatives to find the rate at which the flow rate is decreasing at that specific time. We insert f prime 2 equal to negative 6 exponent to the power of negative 0.3 times 2, and we will get f prime 2 equal to negative 6 exponent to the power of negative 0.6. Then we will calculate the function using the exponential function, which is exponent to the power of negative 0.6 equal to 0.5488. We then need to substitute this value into the equation. We will do f prime 2 equal to negative 6 times 0.5488, and we will get negative 3.2928.
Hello, Assalamualaikum. My name is Muhammad Arman bin Azmi, metric number AA230933, and I'll be guiding you through the problem statement for part B. In a power plant, a cylindrical pipe in a heat exchange system is subjected to varying temperatures, causing it to expand or contract. Although not a sphere or cube, consider the pipe's cross-sectional area, which is circular and thus relates closely to the sphere's geometry. The diameter of the pipe increases at a rate of 0.01 cm per hour due to thermal expansion. Calculate the rate at which the cross-sectional area of the pipe is increasing when its diameter is 50 cm. Discuss the implications of this expansion on the efficiency of the heat exchanger system.
Expanding a heat exchanger typically enhances its efficiency by increasing the heat transfer surface area, allowing for more effective heat exchange and reducing the required temperature differences between fluids. This can lead to improved thermal performance, lower pressure drops, and reduce energy costs for pumpings. However, it involves higher initial investments and potential adjustments to system integration and maintenance. Balancing these factors is crucial to ensure that the benefits of the expansion outweigh the costs and complexities.
The cross-sectional area A of a cylindrical pipe with diameter D is given by the formula A is equal to pi multiplied by D over 2 squared. A is equal to, and also we can use A as equal to pi D squared over 2. Next, we can differentiate the area with respect to time, which is dA over dt equals to d over dt pi d square over 4. Applying the chain rule, we get dA over dt equal to pi 4 multiplied by 2d and multiplied by dd over dt, which give us the value of pi d over 2 multiplied by dd over dt. Since dA over dt is our dA over dt equal to pi d over 2 multiplied by dd over dt is our formula to find the value of dA over dt. We can now insert the value which is given, which is diameter d is equal to 50 cm and the rate of change of diameter dd over dt, which is 0.01 cm per hour. So we put in the value of d and dd over dt into the formula we just made, which is dA over dt equal to pi multiplied by 50 over 2 multiplied by 0.01, which give us 25 multiplied by 0.01, which then again give us 0.25 multiplied by pi. Since pi is fairly equal to 3.1416, we can find the value dA over dt, which is 0.25 multiplied by 3.1416, and which give us the answer 0.85 cm per diameter per hour.
Assalamualaikum warahmatullahi wabarakatuh. And my name is Muhammad Adam Daniel Zamri bin Abdul Azim. My matrix numbers AA2308883. Today I want to present about discussion of this slide. We examine the rate at which the flow rate of oil through a pipeline decrease over time, given by the function f of t equal 20 exponent power of negative 0.3t. By differentiating this function and evaluating it at t equal to 2 hours, we found that the flow rate is decreasing at the rate of approximately negative 3.2928 barrel per hour. Conclusion: understanding the rate of decrease in the flow rate is essential for effective pipeline management. It enables the operators to anticipate and address potential inefficiencies or issues within the system, ensuring optimal performance and reducing operational disruption. Regular monitoring and productive maintenance based on this insight can help maintain a steady oil supply and enhance the overall efficiency of the pipeline operation. For the summary, in the next context of the power plant's heat exchanger system, we investigated the impact of thermal expansion of the cross-sectional area of a cylindrical pipe, given that the pipe's diameter increased at a rate of 0.01 cm per hour. We calculated the rate of increase of the cross-sectional area when the diameter is 50 cm, finding it to be approximately 0.785 cm per square per hour. That's all from me.
In conclusion, derivatives are vital tools for analyzing the rate of change between quantities, particularly in relation to time or other variables. The chain rule enhances this by allowing us to calculate the rate of change of one variable with respect to another, when both are dependent on a third variable. By using this principle, we can comprehensively understand how different quantities interact and change over time, which is fundamental in various fields such as physics, engineering, and economics.